As the last link in our abstraction process, we reached the notion of a topological space where we take the specification of what sets are open as the point of departure. Since the notion of a generalized distance disappears when we reach, in the abstraction process, the stage of topological spaces, now we said, well, we need some counterpart for epsilon balls in metric spaces. And we decided, well, to use the notion of a neighborhood, which would actually exhibit the function of an epsilon ball. Let me start by reminding you of the definition of a neighborhood. Now we start with the topological space. We take a point in the space and we take a subset of the space. Now we say that U is a neighborhood of X if there is some open set G. Remember, we have only open sets, nothing further than that, such that it contains X and is contained in U. Now, before proceeding any further, let's note down some properties of neighborhoods which are almost obvious, but we need them recorded. So let X tau be a topological space again, and X in X. Now the first statement is, if G is an open set containing X, then G is clearly a neighborhood of X. Now here, you can take as the open set G, this G is contained in itself. This is just containment, not proper containment, okay? So every member of X is also a member of U. These two sets can be equal to each other. Secondly, if U is a neighborhood of X and U prime is a superset of U, then clearly U prime will also be a neighborhood of X, because the open set G containing X contained in U will also be contained in U prime. Then U prime is also a neighborhood of X. Finally, let Xm be a metric space X a point in this space and epsilon positive. Now the epsilon ball about X with respect to M, well, the notion of a neighborhood actually came into being as a generalization of this. We expect this to be a neighborhood of X. But that will obviously be so because this is open and contains X. By statement 1 here, it's a neighborhood of X. Is a neighborhood of X. I will just write obvious. Since we will be using these without making any reference to anything, it's good to have them recorded. Now that takes us to our next section. I forgot what the number is. So that actually will deal with a classification of relationships between a point and a set in a topological space. So here we will formalize what it precisely means for a point to be arbitrarily close to a set. We'll reach that stage in this section. So here, the interior closure and boundary of a set. Now, let's start right away with definitions. Let X tau be a topological space. A subset of X, and X a member of the space. Now we will define different relationships between this point X and this set cap A. We say that X is an interior point of A, if. Now, let's remember our pictorial questionnaire. Now, we decided this set to be open, pictorially, intuitively, and we introduced a yardstick. While each point here should allow an epsilon ball about it, which entirely stays within the set. But here, we're in a topological space. We have no epsilon balls. But an epsilon ball, the notion of an epsilon ball, that's now replaced by that of a neighborhood. So, well, then the counterpart would read, this is an interior point of A, X, if X has a neighborhood U, which entirely stays within the set A. But that's equivalent to saying, if X has a neighborhood U, entirely staying with the set A itself is a neighborhood of X as well, since it's a superset of the neighborhood. But that also meets the requirement that there is a neighborhood of X which entirely stays with A. So we'll take that shortcut and define this if A is a neighborhood of X. Secondly, we will say that X is a cluster point of A if. Now here, the everyday meaning of the word of cluster point, well, X should be such that no matter how small a neighborhood of that I take, it should contain points from the set cap A. So it should be a point about which points of cap A cluster. Now, one way of doing that is, well, I can define if for every neighborhood U of X, U contains points from cap A. But I wish to be more careful, and I wish to exclude the following. Suppose our set consists of this and this point. Now, this will be a point of the set, but it will be isolated. So it's not a point about which, if we disregard the point itself, there are no other points of the set which are close to this. So I do not wish to refer to such a point as a cluster point. Thus, what I'll require is, I will make the modification to exclude this point from being a cluster point as follows. If for every neighborhood U of X, one has that this neighborhood X taken out intersection A is non-empty. So actually other points of the set cluster around X. So this now will be excluded because I can find a neighborhood about this. If I take X out from that neighborhood, then no other point of cap A will be left there. But we also wish to specify, to give a name to such points. Thirdly, this is an isolated point of A if, well, now, there is some neighborhood of X which contains only X from the set A. If there is some neighborhood U of X with, but this means that U intersection A, that should consist of X only. Now, a cluster point of A that may or may not belong to the set. You might, well, if this, for example, here is a cluster point of the set pictorially, because whatever neighborhood of this I take and take X out, X itself is not in the set cap A anyway, it has a non-empty intersection. But if I take a point in here, well, that will also be a cluster point, because no matter what neighborhood I take here, I'm drawing the picture having the usual metric in mind. Okay? Isolated points, on the other hand, by definition, they are members of cap A. Now, I will refer to a point X as a limit point of A if X is either a cluster point or an isolated point. Also note that if X is an isolated point, this definition excludes it from being a cluster point. It cannot be a cluster point, because I can take this particular neighborhood U take X out of that set, what remains has an empty intersection with A. So an isolated point is not a cluster point. Well, a cluster point is not an isolated point either. Finally, let me write it here, 5. Well, in this pictorial questionnaire, the yardstick one used was what happens, how the boundary is related to the set. If the boundary had an empty intersection with the set, pictorially, well, we decided to refer to the set as open. If the set contained its boundary entirely, then closed. If none, contains some part and excludes some part of the boundary, neither open nor closed. So we're interested in formalizing what the boundary of a set is. So X is said to be, we say that X is a boundary point of A if, now, if I take this is an open set. Well, this is a boundary point, although it does not belong to the set itself. Here, this is a boundary point as well. Okay? Now, what's the common property of these points? Now, no matter what neighborhood I take of this point or of this point, it will have a non-empty intersection with both the set itself and its complement, what does not belong to the set. It will contain both points from the set and points which do not belong to the set. So that I'll take as the definition for any neighborhood U of X. One has U intersection A is non-empty and U intersection X minus A is non-empty. Now, we refer to the set of all interior points of A as the interior of A, denoted by we use this symbol, or we simply write int A. Now, we refer to the set of all limit points of A as the closure of A, and that will be denoted by A bar or CLA. Finally, we refer to the set of all boundary points of A as the boundary of A, which will be denoted by either by del A or here, the naming in the first and in the last case, well, that's clear. Interior points, well, the totality of them, the interior. Boundary points, the totality of them, the boundary. But here, it's not that clear why we refer to this set, to the set of all limit points, as the closure. So while this set will turn out, and we'll see that today, the smallest closed set which contains A. So if the set itself is closed, its closure will be itself. But if it's not closed, then the question will be, can we extend this set by possibly adding new points to it, but that in the most economic way, such that it becomes a closed set? And well, the answer to that question would be the set of all limit points. You include all limit points which are not in the set to the set itself so that it becomes closed, but it's not obvious from here. Now, two questions. Well, I said, well, we have here a list. Now, which one of these 5 notions actually formalizes that a point is arbitrarily close to a set given? That will be the notion of a limit point. But here we have defined the limit point in a rather indirect way. Well, either a cluster point or an isolated point. But if I had posed the following question, well, let's formalize, given a point, given a set, let's formalize in terms of neighborhoods when that point is arbitrarily close to the set. The natural answer to that would be, well, no matter what neighborhood of that point we take, if that has a non-empty intersection with the set, then it's natural to refer to that point as being arbitrarily close to the set. But that's not the definition here, but it's very easy to see that this description of any neighborhood of that point having a non-empty intersection with the set, that's equivalent to the definition in here. Now, first we'll go quickly through that, and that will be our answer to the formalization of a point being arbitrarily close to a set, the notion of a limit point. Secondly, well, we will turn back to a metric space. Well, then we should be able to characterize each of these points in terms of epsilon balls as well, and that would be useful because when we're in a metric space, we can just confine ourselves to epsilon balls. And secondly, we'll do that. Then we'll see several examples of points and sets and pertaining to the relationship between them. Now, let's start with the simple proposition which I just declared. Let's take a topological space, a set, and a point. Now, X is a limit point of A if and only if for every neighborhood U of X, one has A intersection U is not empty. Although simple, let's go through the proof of this. But let's do it together. Now let's start by assuming that X is a limit point of A. Now our definition is it's then either a cluster point or an isolated point. By definition, X is either a cluster point or an isolated point. Now, what are we supposed to do? Well, we will show that this right-hand condition for every neighborhood U, well, it is satisfied. So let us take any neighborhood U of X and show that A intersection U should be non-empty, no matter whether X is a cluster point or an isolated point of A. Take any neighborhood U of X. Now, if X is an isolated point of A, by definition, X is a member of cap A. When X is an isolated point, of A, X is in A, so that X is in U intersection A, because U is a neighborhood of X, it contains X, that is U intersection A, that's non-empty. Now let's consider the other possibilities. When X is a cluster point of A, by definition of a cluster point, U is a neighborhood, then U minus singleton X, X taken out, that has a non-empty intersection with A. U that's non-empty. But U intersection A contains this set, so it's non-empty as well. Thus, U intersection A, which is larger than this has a non-empty subset, so it's non-empty itself. So we have dealt with the only if part, the left-hand statement that implies the right-hand statement. Conversely, assume that for any neighborhood U of X, one has U intersection A is non-empty. Well, we need to show that X in that case is either a cluster point or an isolated point. Now, let's consider the case where it's not an isolated point. If that implies that it's a cluster point, we will be done. Now assume that X is not an isolated point. But that means for any neighborhood U of X, we have this on the one hand, but moreover, for no neighborhood U of x, u intersection A will be equal to the singleton x. Because that would mean that x is an isolated point. If x is not an isolated point, then there is no neighborhood u of x such that that intersected with the set A yields singleton x. Now, for any neighborhood u of x, let me write it in full, we have both u intersection A is not x, singleton x, and u intersection A is non-empty. Now, if we have both of these, well, then this will contain some points, but it cannot be the singleton x. Thus, it will contain other points of cap A other than x. Points of cap A other than x. So, but that simply means u, if I take x out and intersect with that A, that will be non-empty. But this simply means for any neighborhood u of x, we have this. But that's just the definition of x being a cluster point of A. Thus, x is a cluster point of A. Completing the proof of this. So the notion of a limit point really formalizes, makes it precise, what it means for a point to be arbitrarily close to a set. Now we have this. Now we'll see what the use of that is. Next, let us consider the second question I just mentioned. What form all these definitions take when we confine ourselves to a metric space. So, proposition let Xm be a metric space A, a subset of X, and X, a member of X. 1. X is an interior point of A if and only if. Now here we can take our very first pictorial description. If for every epsilon, the epsilon ball, if there is some epsilon such that the epsilon ball about X stays within the set, because A being a neighborhood of that, in metric spaces, it reduces to that. If and only if there is some epsilon positive such that the epsilon ball about X with respect to M is entirely contained in A. Secondly, X is a cluster point of A if and only if. Now here we have the definition in terms of neighborhoods. What we expect is, well, if we replace a neighborhood by an epsilon ball, it will. For every epsilon positive, if I confine myself from the family of neighborhoods to the family of epsilon balls. Any neighborhood corresponds here to any epsilon positive. The epsilon ball about x, but now x taken out from there, intersection A, that should be non-empty. Thirdly, x is an isolated point of A if and only if, well, here for some neighborhood U, the intersection of U with A should be equal to the singleton consisting of x. Well, then here we'll replace neighborhood by an epsilon ball. If and only if there is some positive epsilon such that the epsilon ball about x with respect to m intersected with A, that's equal to the singleton x. 4, x is a limit point of A, if and only if. Now here, in the definition we had either a cluster point or an isolated point. Well, we can take the disjunction of those, but let's utilize this characterization and let's translate this into terms of a metric space, while here a neighborhood U will be replaced by an epsilon ball. If and only if, for every epsilon positive, one has the epsilon ball about x with respect to m intersection A is non-empty. Finally, x is a boundary point of A if and only if well, again, for every neighborhood, that will be replaced by for every epsilon positive. One has that this epsilon ball about x, that will have a non-empty intersection with A, and this intersected with the complement of A, that will be non-empty as well. Now, these are all simple, but I will leave that as an exercise to you. Well, just go quickly over them and see that you master everything. Now, that takes us to examples. Now, let's first start with an example in R2 and the usual metric D, so that we can use our pictorial intuition. And then we'll pass to examples which are a bit weird. Okay. Now, example 1. Now let's take R2 together with this usual metric. That's our metric space, or that's our topological space. Now let A be equal to the set of all xy in R2 say such that x squared plus y squared is less than 1 and x is larger than or equal to 0. And let me add to that something further, because I wish the example to be such that all the notions here have a counterpart. This will have no isolated points, for example. And let me take it as 1 over n minus 1 comma 0 such that n is in n. Let us first draw the picture of this set. We have the xy plane. Now, x squared plus y squared, that equal to 1. That's the circle about the origin with radius 1. But we take only this part and we exclude. This is 1, this is minus 1, this is 1. So we exclude the circle itself. This is excluded, but this is included in the set, okay? Because x is larger than or equal to, right? Then here, if n is 1, you get 0, 0. This is included. Well, then, if that's 2, minus 1/2, 0, and then you get all these points. But minus 1, 0, that's not included in the set, okay? So that's our set A. Now, what's A interior? I will just go through the check in pictorial terms. Well, everything in here, except for points on this portion of the y-axis, they belong to the interior. But points on here, they belong to cap A, but they do not form interior points because no matter what epsilon ball I take, that will not entirely stay within the set. So here I'll have xy in R2 such that x squared plus y squared is less than 1, but x is larger than 0. X is 0, they corresponds to points on the y-axis. That's excluded. And no point from here is an interior point either, because if I take epsilon balls about this, they will not stay within the set. Now, let's find cluster points away. Now, all interior points, they're cluster points as well, because no matter what epsilon I take, if I take the center of the ball away, that will have a non-empty intersection. But if I take a point here, that will have the same property. No matter what epsilon ball about that I take, this will have a non-empty intersection with the set. Points on here, they will as well. But what about these points? Well, they will get closer to each other, but no matter how close, I can draw about each of them an epsilon ball, which contains just the center from the set and none of the others. So these will be isolated points actually, but they will not be cluster points. But is there another cluster point which is missing, which I have not gone through? It's -1, 0, this point. This point itself does not belong to the set, but no matter what epsilon ball I take, no matter how small, it will contain points from this part of the set. Well, the center, that does not belong to A itself anyway. If you discard that, the intersection will still be non-empty. So we can write this as xy in R2. Anything else, they will not be cluster points. Because for cluster points, we have to consider the candidates are all the points in the space, not only the points in the set, but also those outside the set. This will be x squared plus y squared less than or equal to 1, x larger than or equal to 0. This takes all this part, but then also union -1, 0. I guess we can take a break now. We'll continue with the rest next hour.